Okay, so it's time to finish this lecture one on the overview of what we are trying to solve, and this is what we are going to do now. We last time in the previous screencast, we showed that we can have what is the Hamiltonian operator and how we can separate the electrons and the ions. So it's called the Born-Oppenheimer approximation. We've done that. Then we ended up with an equation like this, which is the electronic problem. So now we have separated the ions from the electrons. Think about this image of the birds flying so fast around the elephant. Okay, the first term here is, again, the kinetic energy for the ions. The second term is what we call the external potential. I've insisted on this, but I will again. This is now considered external. This is really, in our case, the interaction between the electron and the ions. This is not necessarily an external field that we apply or a magnetic field or anything like this. This is really what's external to the electrons, not just external to the system. Okay, I hope it's clear. The next term is the interaction between the electrons. Now, you can see that the operators that we have, of course, here the operator look like function when we work in XYZ coordinates or differential operators. We can see that we have a one body problems on the left hand side. These are one body interaction. They only, when we say one body, that means that each of these two terms, the first two terms, only involve the coordinates of one electron, while the third term involves the coordinate of two electrons at the same time. So that's why we call the many body Hamiltonian. Now you can say, well, it's just only two bodies. Yeah, it's pairwise, but we sum over all the pairs, right? So this is actually the bit that's complicated. In the next few minutes, I'm going to talk to you a little bit more about each term because it's so important. The first one is the external potential I want to tell you about. So the external potential is due to the presence of the ions. It is a positive term here in the sense that it's actually it turns out it's in this case there is a negative sign because of the charge. The difference, the Q and Q are a different sign, so it's actually a negative sign. It's it's a negative term. Um, it's related to the electrostatic interaction between an ion position at RK and um, and an electron position at Ri. So I'd like to insist that RK here is not a variable; it's a parameter. So basically, you are given this parameter, which is those parameters which correspond to a configuration of ions, and then you get to calculate the rest. All right. So these are parameters. Now the ugly part of the whole thing is called the electron-electron interaction. In fact, if there were, there are two things to say. First of all, if there was no electron-electron interaction, the problem would be trivially easy to solve. So you may be sad about that, but don't be, because if there were no electron-electron interaction, there would be no interesting physics in that area of condensed matter physics. Most of the fun part in condensed matter physics really come from the electron-electron interaction. Of course, this is hard to get, but usually, the best dreams are the hardest to get, right? So this is complicated, and it's actually related to the electrostatic interaction between electrons. And you will see why it is so complicated to solve. But to give you already an idea, even solving classically the many body interaction between planets in the solar system is an impossible task analytically. And here we are just, and there we are just talking about a few celestial bodies. Here we are talking about a very large number of electrons that interact. It's a very complicated problem. This is exactly what DFT is about. So sometimes we call them correlation, and I'll come back to the definition of what we mean by electronic correlations. Essentially, I mean, I like this plot that I found on the internet a few years ago. That was about if one electron is modified somewhere, is affected somewhere, it will affect electron at all many other places. That's basically what the correlation is. In a way, And that effect is done in a way that's actually pretty significant. Now, the last term I didn't tell you about, which is an important term as well, is the kinetic energy. So the kinetic energy, again, here we don't use atomic unit, which in atomic unit, the h bar square over m would be equal to 1. It's a detail that I don't want to spend too much time about. This is a one-body interaction, but there is a little something I want to tell you about. I mean, it's always very useful to do. Imagine that you have a large kinetic energy. So if you have large kinetic energy, the uncertainty on the kinetic energy is large. And according to the Heisenberg uncertainty principle, if you have a large uncertainty on the kinetic energy, you have a low uncertainty on the position. So a large kinetic energy term will actually correspond to a more localized electron. It may seem a little bit counterintuitive. One example to make it a little bit more intuitive is that the bodies that are the faster system, the faster electron, for example, in the hydrogen atom, are the ones that are the closest to the nucleus. Why are they the faster? Because they are the ones that experience the largest attraction because they are so close to the nucleus. Now, there is another thing that I like to always think about is that there are sometimes people who prefer to think in terms of math. In terms of math, what is a Laplacian? Well, a Laplacian basically measures the curvature or the spread of a function, right? So it basically provides you the idea of how spread things are. So that basically tells you that if you have something that's really spread out, you are going to have uh, uh, so basically not moving fast. That means that the Laplacian will be small, and in that case, if it's small, that means it's spread. That means there is no localization. And the other way, on the other side, if it is not spread, so it's very localized, the Laplacian will be very large, and therefore it's going to be also localized. So there is a way to think a little bit about Heisenberg principles, looking at the math, looking at examples, but try to convince yourself that in kinetic energy, if the kinetic energy is very high, that means that you have strong localization. Personally, I find that when I learned this, I found that a bit counterintuitive. I would think that if something can move fast, it should be delocalized, but it's not the case. That's not the correct way to think about it. I mentioned to you relativistic effects. Relativistic effect is sometimes that velocity I just mentioned to you could be too large. Uh, could be so large that it's a fraction of the speed of light. In that case, we do have to worry about relativistic effect, uh, like in the hyperfine description of the hydrogen atom. This can happen in large nuclei, like gold, for example, and other material like this, because you have such a large number of atomic charge of the charge of the ion that the attraction of the electrons that are closest to it is so large that the velocity is super large and very close to the velocity of light, speed of light. In that case, we have to worry about this and solve Dirac's equation. We are not going to be concerned too much about this. I will explain to you how those relativistic effects are taken into account in DFT when we talk about pseudo-potential. So let's not worry too much about this point, but know that I'm not ignoring it and I'm not sweeping it under the rug either. That is a fundamental observation I want to make. Let's go back to that equation. I explain each term separately. At this point, you should feel comfortable with this equation. The very fundamental observation is this one. These two terms in blue are universal functions, or universal operator. In other words, they do not depend on the position of the ions. There is no parameters of the ionic position in there. These are operators that exist no matter what the system. So they are universal in that sense. So they are properties that do not depend, at least not explicitly for sure, of the position of the ion. On the other hand, the external potential, this one, is system dependent. It is not non-universal. So if you calculate this equation for gold or for graphene, the blue term will be definitely very different. Now, the question you can ask yourself is, where do the many body effects come from? So the many body that are interested. Well, if you followed, you already know the answer because I already gave you the answer. They come from the electron interaction. Because the only term in my Hamiltonian now that involves more than one body, again, treated explicitly, as opposed to the electron-ion interaction, which is not a many-body interaction because the ions are treated as parameters, as basically setting the stage, if you will. But in the case of the electron-electron, this is a true many-body effect that comes from the fact that you have electrostatic repulsion between them. But at the same time, you could say, well, fine, they you just go fly away and then you minimize that interaction. Yes, but at the same time, they also want to maximize or optimize the interaction with the positive ion. So at some point, they don't want to be together. It's like a bit like people at a party. Some people don't like each other, and still they meet each other at a party because they're attracted to go to the party, and yet they don't want to be together, but they end up interacting anyways, right? So in this case, it's basically the same. The electrons come to a party, attracted by the ions. They are not. There is no attraction between them. There is actually a repulsion, but they still interact, right? They have to interact because they want to be at the party, which means in this case being around the ion. So what we usually do in quantum mechanics, and so far we have not really done any density functional theory. I've used the word a lot, but we have not done any. Is this? So I'm summarizing what we have. We are given an external potential because remember the other terms are universal. We're given an external potential with all the position of the ions. We solve Schrodinger equation, the time-independent Schrodinger equation. We get the wave function. And then we know that we can calculate observable by calculate those brackets or those matrix elements, and then we get observables. So we can get like dipole moment, like I don't know, positions, that kind of things, and then we get all the information we want. So we specify the system with the external potential V of R. We plug it into the Schrodinger equation, and then we solve the wave function. And that way, after that, we can get the expectation value, which basically is your handle to to experiment, so to verify that what you calculated actually makes sense. So let's just pick one example of observable. One observable is the electron density. What do I mean by that? Can I see the electrons? Actually, you can. With techniques such as scanning tunneling microscopy, you can actually look at the density of electrons. That's one way to do it. So STM, scanning tunneling microscopy, which was developed in the 80s, not a Nobel Prize in physics, this case, for that development, from Binnick and Rohrer. So the density is obtained by this. It's the definition essentially of the density, which actually this is the formula of the density, which gives you the probability of finding electrons at position R, R2, and so on and so forth. So this one here, what is the probability of finding an electron at position R? For that, it's all the probability of finding an electron at position R with all the electrons being everywhere else. That's basically what it means. So this is actually an important equation. I don't want you to take it for granted. I'm going to demonstrate to you how we get there. It's actually pretty straightforward, so that's why I'm going to do it. Okay. The first line here means that the density is essentially the expectation value, so the matrix element of this sum of Dirac delta, which tells you the position of an electron at position R, including all the position of the electrons I in the system. Now, once you have this, you can develop these brackets using all these brackets using the definition of the completeness relationship of the position, the basis function for the position. Then you develop this, and at the end, you find exactly this equation here. So if you do not remember how to do this, you can do two things. First of all, you take the result for granted and you're happy with this, or you take a minute, you pause the screencast and you redo the calculation just to convince yourself. How do you solve the many-body problem? Well, the answer is that not easily. So people are working on many ways to do this. Some in physics, for example, we try to do this using perturbation theory. For example, Feynman diagram and Green's function is an example of perturbation theory. Chemists are using other methods like configuration interaction method, couple cluster, and all sort of things. And they know how to do this in very small system by considering those advanced many-body problem issues. So there are different techniques. They are not always very practical because they take a lot of computational power and it's becomes very tedious. So, for example, there's one example which is quantum Monte Carlo, which is a beautiful technique to do these kind of things, but you can only look at a number of number of problem there. It's related to sampling, but we are not doing that here. That's what the density functional theory is not. Is another method. So how difficult is this anyway? Before we move on, this is the equation we are trying to solve. Now imagine for a second that you want to solve this, and you want to define. You don't want to use R, the R position, R1, R2, as continuous function, but let's say that you want to discretize it on a mesh, just to make the problem simpler. So imagine that you want to describe each of them on 20 mesh points, which is actually very sparse, but imagine you want to do that. Imagine now that you have, let's say, n electrons. Each electron, of course, has 3 coordinates, x, y, and z. I'm not even going to worry about the spin here. And therefore, if I want to describe this with each position described by basically 20, each degree of freedom described by 20 grid points, the total number of grid points I have to describe that wave function will be 20 times 20 times 20, this 3n times 20. So 20 to the power 3n, okay? So that's what the number of points I need. And again, remember, it's only using 20 points for each coordinate, which is very sparse. So, so this is actually a problem because for the wave function, that's if n is like, let's say n is equal to 10 electrons, I'm going to use 10 to the power 20 to the power 30, which is totally impossible to do on any computer. Now imagine for a second, and I've not proven that to you yet, that you could use a density instead of the wave function. So density functional theory is really that, is that you can use a density. So imagine you could use a density instead of the wave function. The density is a function that only depends on 3 coordinates, x, y, and z of electron. So in that case, you could represent the density of 20 to the power 3, right? 20 for each direction. So that would be 10 to the power 35 less time or less memory that you would need. So basically it would make it possible. But not only it would make it possible, it also tells you that you could not really solve for the wave function this way. So this is really a complicated problem that we are trying to solve. So in a nutshell, DFT provides an alternative. It could be less accurate, that's what we are going to describe, but we are going to explain how it can be done. So we also know in DFT that I insisted on that really what is not universal in the quantum mechanical description is the external potential, and we are going to use that. By the way, when I say operator T is the kinetic energy and U is the electron-electron interaction. So we are going to show that DFT provides a way to solve the many-body problem. That's what this course will be all about. And then we will demonstrate that formally that the density is all you need. So it turns out that today when you want to do calculation to understand a material or a chemical or anything like this, there is a 99.5% chance that DFT has been used for that. Okay, so this is what we are going to do. So the last thing I want to tell you is to give you kind of a is to give you an idea of what we are going to do. And I've not proven it to you, but I will. That what we can do is to make that the knowledge of the density is enough to know wave function and potential, and hence the observable. And even more than that, we do not need to go through the wave function. And this is really the big deal about DFT. You do not need to calculate the many-body wave function. All you need to do is to be able to calculate the density itself, and with methods that, for example, are based on the Coin-Sham theory, which we'll show in this course. So that I hope that this introduction to the problem will be useful to you. We are going to study a little bit more the chemistry, the wave function method in the next screencast, and then we'll dive deep into DFT. Thank you very much.